Welcome. Today we are diving deep into a massive topic in chemistry, acids and bases. You see them everywhere, from the food you eat to the products you use, and we're about to break down exactly how they work from the ground up. Ever find yourself scrolling through past exam papers and just feeling totally swamped by this topic? Yeah, you are definitely not alone. It's a big one, but that's exactly what we're here for. In this explainer, we're going to connect all the dots, from the basic theory to actually solving those tricky exam problems. So let's start at the very beginning. Can't build a house without a foundation, right? We're going to quickly cover the absolute essentials you need to know to make sense of everything else. When you get right down to it, it's all about what happens in water. It's a tale of two ions, really. Acids are all about producing hydrogen ions, H+. That's their signature move. And on the other side, you have alkalis, which are just bases that can dissolve in water, and they produce hydroxide ions, OH-. They're basically chemical opposites, perfectly designed to neutralize each other. Okay, now here's a point that trips up so many people: the difference between strong and weak. This has absolutely nothing to do with how concentrated a solution is. It's all about how much it breaks apart or dissociates in water. A strong acid completely falls apart, releasing all of its hydrogen ions at once. But a weak acid, it's a bit more reluctant. It only partially dissociates. It's a super important difference. Next up, we have to talk about an acid's potential, and we have a specific word for that: basicity. It sounds a little strange, I know, but all it means is this: how many hydrogen ions can one single molecule of an acid donate? So hydrochloric acid, HCl, has 1 to give, it's monobasic. Sulfuric acid, H2SO4, has 2, it's dibasic. And this little number, it's going to be absolutely vital for our calculations a bit later. So we've got the core concepts down. But how do we actually put a number on acidity? How do we measure it? Well, that brings us to our next tool, the pH scale. The pH scale. It's our go-to for measuring acidity. Now, the key thing to remember is that it's a logarithmic scale. That sounds fancy, but all it really means is that for every 1-point drop on the scale, the acidity actually jumps up by 10 times. It's an incredibly clever way to take a massive range of possible concentrations and squeeze it into a simple, handy 0 to 14 scale. So, in an experiment, how do we see when a reaction hits that perfect point of neutralization? We use something called an indicator. And let me tell you, you will see these two all over your exam questions. You've got methyl orange, which goes from red in an acid to yellow in an alkali. And then there's phenolphthalein, which is colorless in acid and turns this brilliant pink in alkali. You've just got to know these. They're the visual clues that tell you when to stop. Okay, enough theory. It's time to put it all into practice. Let's talk about probably the most important experimental technique in this entire topic. Let's talk about titration. At its core, titration is like a piece of chemical detective work. It's this super precise method where you use a solution you know everything about, its concentration is exact, to figure out the unknown concentration of another solution. The whole goal is to find that one precise moment of neutralization. And the procedure itself is very systematic, very step-by-step. First, you need that standard solution with a concentration you know for sure. Second, use a pipette to move a very specific volume of it into your flask. Third, you slowly, carefully add the solution you're testing from a burette. And fourth, you stop the second you see that permanent color change from your indicator. That's your endpoint. Now listen up, because these are classic mistakes pulled straight from past papers. First, never rinse the conical flask with the solution you're about to put in it. Why? Because you'll be adding extra unmeasured moles and your entire calculation will be wrong. Second, don't leave the funnel sitting in the top of the burette. If a single drop falls in after you've taken your reading, your volume measurement is inaccurate. You got to avoid these pitfalls. All right, the absolute best way to understand all of this is to just do it. So let's walk through a real exam problem together, step by step. Okay, here's our scenario. We have a known amount of acid. We know its volume and its concentration, and we know exactly how much sodium hydroxide it took to neutralize it. The mission? Find the concentration of that sodium hydroxide. Pro tip: the very first thing you should do in any calculation problem is get your data organized. Just lay it all out nice and clear. We've got all the info for the acid. For the sodium hydroxide, we have the volume, but that concentration is a big question mark. That's our target. Okay, step 1. We always start with the substance we know everything about. In this case, that's the acid. So let's find the number of moles. It's just concentration times volume. But, and this is key, remember to convert your volume from cubic centimeters to decimeters cubed by dividing by 1,000. Do that and you get 0.00125 moles. Now for the most crucial part of the whole thing, the mole ratio from the balanced equation. This is the magic bridge that connects our acid to our alkali. Because our acid is dibasic, you can see it takes 2 molecules of NaOH to neutralize every 1 molecule of acid. So our ratio is 1 to 2. Now that we have that 1 to 2 ratio, the rest is easy. We can figure out the moles of NaOH that must have reacted. We just take the moles of acid we calculated and multiply by 2. That gives us 0.00250 moles of NaOH. See? We're almost at the finish line. And for the final step, we just rearrange that formula we used earlier. Concentration equals moles divided by volume. So we take our moles of NaOH, 0.00250, and divide by the volume we used, 17.20 cubic centimeters, again, remembering to convert it. And there it is, our final answer, 0.145 moles per decimeter cubed. And there you have it, problem solved. But you might be wondering, okay, great, but why does any of this really matter? Well, this is so much more than just an exam trick. This is a fundamental skill for any chemist. I mean, hey, don't just take my word for it. The curriculum guide itself calls this a vital technique. That's not just filler text. They're telling you that what you just learned is a true cornerstone of analytical chemistry. And they're right. This exact technique gets used every single day out in the real world. We're talking about quality control labs in the food industry, or scientists monitoring the health of rivers by checking their acidity. The precision you're learning here has a real impact. So think about what you just did. You started with a puzzle, right? A complete unknown. And by applying these principles, you figured it out. You've learned how to analyze the world around you on a molecular level. That's a pretty powerful tool to have. The only question left is, what will you discover with it next?